So if you are interested in, because they, yes, for sure, they are important. However, they are the most, not the most important things comparing to the other content of the course. Yeah. And for example, the chapter 8 regarding the business opportunities and of the additive manufacturing, and we have in mind that additive manufacturing has many sustainability advantages go along with challenges. But these advantages are the driving forces that motivate a lot of companies in the world for the moment try to use this technology in order to fabricate the part practically. And one of the reasons is the near shape component and the high degree of automation, which offer you to save the cost and time during the manufacturing process. And this technology is no longer is rapid prototyping, but this can be used in order to fabricate the real part, the real products. So no longer the prototype, yeah. And you can use them practically. And you have the possibility in order to fabricate the part on demand and on-site manufacturing. You can use the many benefits caused by or originated from the digital twins. You can also save the cost of fabricating or building up the physical warehouse, because you know that you can fabricate the part on-site on-demand manufacturing, and it changed the way of logistics, where you do not need to build a physical warehouse just when you need, and just bring the system to the place. You want to print the part out and then, yeah, do it. Because the technologies has its own the high degree of automation, and once you have the machines, once you have the design, which you can download from the database, and the materials and the power as well, and just push the button and everything is ready. Okay, so so yes, but of course new technologies lead to the formation of new type of entrepreneur or new type of company. So DG chronoship, for example, but then just some informations which yes, which is concern the new type of companies occurs as a result of the how can I say, of the era of additive manufacturing, let's say. And now let me continue with the lectures, chapter 6. Okay, I will serve the lecture, so it's going to, I will not focus in detail. Rather than I will tell you how to investigate lectures in the most effective way, let's say. So as I remember last time we stopped more or less here, where we have to consider the parameter selection. So for example, several parameters associated with the scanning process, like for example, the scanning velocity, the height distance, the laser scanning pattern, and the layer thickness as well, and the others. Of course, we have more than 180 parameters. Those need to be considered during the additive manufacturing process. However, among them, those that are important can be the laser power, the spot size, the scanning speed, uh, height distance, and I would say that the most important thing is layer thickness. Because practically when you select the processing parameters, uh, the printer suppliers has already developed the set of parameters for you. So they are somehow the optimized parameters, and these will be defined based on the layer thickness. Unless you want to investigate the set of parameters on your own, otherwise it's better to refer to the set of parameters suggested by the manufacturer or the printer suppliers, and they are referred to the layer thickness. So for each uh, degree of layer thickness, for example, 20 microns or 40 microns, the set of other the set of remaining parameters are defined by the manufacturers, and you should refer to these parameters rather than developing on your own, because it's a matter of time, cost, and effort, yes, of the researchers at the company as well. And for the laser, in the chapter 3, you were introduced about the heat source for the additive manufacturing, especially need when you use the direct energy depositions or the powder bed fusion, where you use, let's say, the laser, the electron beam, the plasma art as heat sources. Yeah, and you have the equation, and I do believe that we also investigate the equation to a certain extent, and by increasing the distribution factor F, we have the energies which is more focused and the high peak of temperatures underneath the heat source. This means that is better because we can concentrate or we can focus the heat source to a small spot size and heat up the material up to the molten state, and then we have the molten pool. Yeah. Uh, but if the energy is transferred to the materials uh, insufficiently, and in that case you will have some type of a defect, which will be mentioned to you in the next few slides. And the powder bed fusion use the common beam diameter on the order of 50 to 100 microns. This is considered at the fine resolution, and direct energy deposition use larger beam. Yes. So faster, but then you faster the process, but you would have poorer quality, at least referring to the surface roughness. Surface roughness. And you also have the relation between the laser power, volumetric heat input, and so on. And if you investigate a certain paper regarding the additive manufacturing, you may be familiar with this equation, informing the relation between the laser power, volumetric heat input, and so on. Yeah, it can help you somewhat in understanding the appropriate parameter selections. And here, um, the figure on the right side of the slide inform you the relation between the source power as a function of scanning velocity, but just providing you the idea of, for example, if you apply the high power source, yeah, high source of power with low scanning velocity, what type of effect you would expect to have. Uh, so for sure, you need an appropriate combination of the source of power and the scanning velocity in order to be able to receive the fully dense path. That's what we would like to have and to do. But out of this, let's say, reasonable range, and you would have some kind of effects like porosity, Bowling effect. Bowling effect when you apply a high power source together with a high scanning velocity, and if you apply the low power and high scanning velocity, it means that uh, the scanning speed is uh, too fast, that the energy is transferred to the material insufficiently in order to melt the material. So you have the lack of fusion. So which is fused not enough, and you have a lot of porosity between the powders. So the powders do not melt completely, and you have the, of course, let image that you have the powders in the spherical shape, and even you pack them together, there are certain porosity in between powder surfaces and the other porosities. So key factors, well, for example, you need to pay attention to the laser power, laser scanning velocity, the laser beam profile, of course, the intrinsic properties of the material as well. This means that the interaction between the heat source and the powder bed. And yes, so basically you should reduce the laser power and increase the scanning speed. Should, but it depends on the situation. Yeah. If the laser path on the scanning pattern increase the drill time, it means that the time that the laser focus on a certain area of the powder bed, meaning that you increase the energy density and can lead to the formation of keyhole porosity. Yes, because the high enough energy is provided to the powders, and you may have some kind of material evaporation or the gas with pressure, which induce the keyhole effect there at this position. So lack of fusion porosity depends on Melbourne scanning pattern. Scanning pattern is how you let the laser scan through the surface of the powder bed. It can be the unidirections, zigzag, 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 yes, and so on, and islands. Yeah. During the additive manufacturing process, you must select the layer thickness which is smaller than the mean depth overlap to prevent the negative effects of lack of fusion. So you could see that, for example, you have the two scanning line, and if you see the surface of the screen, and then the centers of the curve, yes, the center of the curve is something is the position where we let okay, the spot side go through, and the how can I say, the curve which represent the boundary of the region, showing probably the heat affected zone, heat affected zone. So it means that within the gray color regions, the heat will be enough to provide to melt the materials, and you have the overlapping regions. Yes, overlapping region where the how can I say, where the depth, yes, where the depth of the overlap region is reduced with respect to the MD regions, and the MD0 should be larger than the maximum thickness of the layers to guarantee that, okay, you can completely melt the layer of the powders, and to provide enough heat in order to connect the new layer with the previous layers. Yeah, this is very important. And if you shorten the hatch distance, the hatch distance is mean that the distance between the two adjacent scanning vector, and if you reduce the hatch distance, shorten, which means that the thickness of the interference region or the overlap region will be increased, and you can somehow fabricating the material with larger thickness. In the other case, when you reduce or you enhance the hatch distance, or you reduce the thickness of the overlap region, and therefore you can fabricate the part with the smaller thickness. Yeah. Other simplified word, okay. By scanning too fast with low power, it means that you provide not enough energy to fully melt the materials, and as a result, you have the lack of fusion. Yes, and the lack of fusion meaning that, okay, in one layer, the material does not melt completely, and therefore we have not enough energies to bond different layers together, and you may have the risk of delamination. So lamination is mean layer on top of the other layer, and you must have let's say the good bonding between layers, but now since the energy is provided to wet the layer is not enough, and therefore you have the risk of delaminations. However, if you apply too much power, you can overheat the melt point. Yes, with the deeper energy penetration, so the energies go deeper into the materials, and this may create a keyhole effect and induce the higher degree of porosity inside the material. Yeah, unfortunately, yeah. The laser power must be enough to fully melt powder. How you define the the sufficient level? Yes, it's not easy. Yeah, you have to do the experiment, or you have to run some kind of simulation in order to predict the how can I say, the suitable values of the laser power go together, combined together with other parameters like the scanning speed as well. High power laser, yeah, combined with fast scanning speed up to a certain level, you can make the well pool unstable to create the boiling up effect. So it's something like droplet, 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 like a bone, like bones. Yes, uh, stand in adjacent to the others. Yes, but this is uh, undesired effect. Undesired effect. We do not want to have this kind of effect. So you see you could see on the in the bottom of this slide the keyhole induced porosity, which means that the porosity and the lack of fusion, and you have the pores or the free space inside the material, which reduce the density and reduce the strength of the materials. And you have to find the appropriate combination of different parameters in order to avoid these negative effects. And here, this is some kind of summary, like tables, summary the problem, the primary approach in order to solve the problem, and the secondary approach, for example. Just explain one. Uh, so, for example, if you have the keyhole porosity, why you have the keyhole porosity? Because you have the high energy source go together with low scanning velocity, and then you can reduce the laser power. So just see on the relationship between the source power and the scanning velocity in order to, I can say, modify the parameters. Like a fusion, you can reduce the scan line spacing, reduce the layer thickness. And why you have this? Uh, the lack of fusion, because if you see the overlap regions, and if the heat, yes, the heat is transferred not enough to the materials, or in other words, if the MD0, if the MD0 is smaller than the maximum layer thickness that you plan to to fabricate, and the energy is not enough in order to penetrate the whole depth of the layers of materials, and therefore on the bottom you may have the not enough energies in order to even sinter the powders, not melt, but even sinter the powders, and therefore you may have the effect of delamination because at the bottom, for example, at the level of Tmax, if the energy is transferred to this depth, and then you can melt this layer and the previous layer, and if not, and you do not have the good wetting between the two layers, and this is a problem which may lead to the material delamination. I'm sorry, just a minute. Yes, and where am I? And composition chains. Composition chain, why? I have mentioned several times to you that if you use, for example, very high power energies applied to the powder bed with very low, let's say, scanning velocity. So this means that the laser spot sign and the laser spot will stay at a certain positions for a longer period of time, and during that time you transfer more energies than necessary to the materials, and the material will receive a lot of high power energies more than expected, and those and this material will be heat up significantly, and this is above the evaporate temperatures of the low melting temperatures elements, and these elements can be evaporated, lead to the composition change or the loss of alloying elements. And in that case, you need to reduce the laser power and increase the laser velocity in order to reduce the energies transferred to the materials. Yeah, and so on. And this is the idea how you can modify the parameters in appropriate way in order to guarantee the how can I say, and the quality of the materials. But then it's necessary to run some kind of simulation, yeah, in order to predict that thing. Or you can do trial and error approach, but it means that you waste a lot of money, time, yes, and effort. Parameter selection. So you could see about the scanning pattern. So we have different type of scanning pattern, not only four as mentioned on this line, actually many. If you if you investigate review papers regarding the additive manufacturing, especially the metal additive manufacturing, you could observe that there are many scanning strategies that can be used in order to fabricate the part additively. Yes, and so far I could say, the Iceland and rotation, yes, uh, is selected widely. Selected widely. Scanning with the square rotation, randomizing the scan orientation, you can reduce the stress, distortion caused by the thermal factor, and promoting the full fusion of the position. And therefore, this is preferable to use the Iceland rotation scanning pattern. The scanning condition can change, for sure. That's the reason that one company in Norway, they have developed the 3D printing system called rapid plasma depositions. So it's something like the direct energy depositions, but this is the plasma as his source, and they have the feedback system that can provide the data 600 data points per second. Yes. So in order to guarantee if there's something changed, and the software can modify the change, or you can adjust, yeah, adjust the change. In direct metal laser sintering process, generally speaking, the scan ranges from 50 up to 2000 millimeter per second. So it's quite fast, but how can I say, electron beam scanning can reach the faster scanning velocity on scanning rate. The exposure time is 0.2 up to 8 millisecond. Diffusion time 40, 80 millisecond, and so on. This information is taken from Material Science Engineering journal written by Simchi. Layer thickness. When you reduce the layer thickness, yeah, of course you can increase the detail of the parts because the accuracy can be enhanced, and therefore you enhance the qualities of the surface after the sintering or melting process. In other words, you reduce the average roughness of the SB part. But at the same time, you have to scan, or you have to synthesize more layers, more numbers of layers of materials. It means that you increase the building time. Yes, everything has two side effects. You have to pay more associated with the time for fabrication. And the surface roughness can be calculated based on this equation, and I will not focus on the investigation of the equation. Where is it? And here, for example, this is some kind of uh, note regarding the primary processing parameters for particle fusion and direct energy depositions. So they are among those important parameters for the fabrication process for additive manufacturing. Beam power, energy density, beam focus, offset or spot size, spacing, of course, and many. And it's quite important to pay attention to the you plate preheat in some situations, because in that case you can reduce the thermal gradient between different regions of the path and reduce the risk of distortion caused by the thermal gradient. Yes, yeah, for sure. And you should control the atmosphere inside the building chamber, and that's the reason that you have to limit the amount of oxygen and water gas inside, and down to several parts per million. some. And if you want to increase the quality of the part, and you should maintain the vacuum inside the building chamber, yeah, to prevent some kind of unnecessary reaction between the material and the gas at high temperatures under the influence of the laser source or electron beam source or high energy sources. Yes, and on the right side you can see that it is the setup parameters for printing in the Autodesk NetFab. I have been screen this window to show you about the laser power and heat shot absorption energies. So, for example, for aluminum or here is inconel, you have a certain amount of energy reflection. This is based on the intrinsic properties of the material. And travel speed, layer thickness is 40 microns. Mass spacing, 160 micron. Record time stood standards 15 seconds, yeah, and so on. The interlayer rotation angle is something referred to. I'll show you here. Is the rotation angle here. You will see on the top right of the slide where you print the material or you scan the laser for each island, and once you finish this layer and on the next layer and you rotate, let's say 67 degrees degree respect to the previous layer, and all of them need to minimize the negative effects. Yeah, the aim is to minimize the negative effect regarding, for example, the lack of fusion and to reduce the porosity, yeah, increasing the bonding between the layers and layers. Parameters optimizations, yes. If you select and based on experience, you can modify or optimize the values of the parameters before the 3D printing process. Yes, but it depends. Here, there's no information regarding the specific values because this information is confidential. But I just provide you some general consideration. So, for example, if you have the excess heat input, so it means that you provide too much energies, you increase the melt point size and solidification stress distortion, and you may have the negative effect of material evaporation for those elements have low melting temperatures, and therefore you may have the loss of deposition accuracy and so on because the material is evaporate, and the effect is something like sputtering, bắn vung té, and it's negatively affect the accuracy of the part for sure. And multiple passes and scan orientation path may apply, to increase the full fusion or to guarantee the full fusion of underlying layers. But then you're increasing the time and the energies because you scan 2 times for the same layer to guarantee the full fusion. Full fusion is mean that to melt completely the layers. Yeah, the quality is enhanced, but then you spend more time and energies for the scanning for each layer. It means that you increase the cost. Energy density is too low, and then you may have the undesired degree of melting. It means that material delamination porosity is too high, and then you may have the void spattering is okay, and vaporization is mean like water vaporize, yeah, okay. So regarding the AM material optimization goals, you can have optimize the goal is to have the design accuracy, density, if possible 100% relative density, good surface finish, heat control. It means that low thermal gradient between different regions apart, to reduce the stress or distortion or maybe the crack risk for the material after the process. Reduce build time, but this you have to find the trade-off because increase the layer thickness to reduce the build time, meaning that you have the larger effect of staircase. And then you have to apply the post machining process in order to make the surface smoother. Like milling process for cutting the residual powder on the surface, yeah, and so on. And if you want to modify the properties, and for sure you may need to apply heat treatment in order to achieve the desired properties when necessary. Yes. And reduce build time depending on factors like thickness of recording layer, overlap between the scan passes. If you increase the overlap between the scan passes or the hard distance, you can increase the thickness of recording layer. Yes. But then pay attention to the staircase effects, because if you want to have the smooth like the black curve, and then you have to apply the post machining to eliminate the residual materials after the sintering or melting process. Increase the hard distance may not fully fuse the current track to next. Yes, because you reduce the MD. You reduce the MD. Or the thickness of the depth of the overlap region is smaller than the thickness of the material that you need to wet, and then you have the problem of lack of fusion, and you have the risk of material delamination. So delaminate, sự tách lớp. And regarding the surface finish, if you have the how can I say, if you provide not enough energies and you have the partial fused powder and partial fused powders, you can see that a lot of powders still stick on top of the material after the selective laser melting process, which look terrible, I would say. Yeah, with high magnification here, and you see that the powder attack on the top of the surface. Yeah, and this if you want to increase the surface finishing condition, and you want to apply, and you may need to apply the post machining process. And the roughness is range from the 300 and up to 600 micro inch for particle fusion. Yeah, is measured in inch. And from 800 and up to 1000 micro inch for particle fusion using electron beam as heat source. In the case of fused wire depositions, like in the case of direct energy depositions, we have the large overlapping bed, large melt pool, high deposition rate, but then cost features. So this has the possibility to enhance the productivity of the process, but then you have the cost feature. Cost features mean that it's quite difficult to fabricate the part in an accurate manner. And you have to apply some additional step in order to fabricate the part in those finer dimensions. AM surface conditions need to be optimized. You need to select appropriate parameters. You need to combine with suitable post-processing steps, and you may need to consider the finishing allowance. This means that you need to add more material than necessary, not so much, but enough for the post-processing step. Yes, and that after the 3D printing, you can cut a small layer of material to increase, for example, the surface to increase the surface quality or reduce the surface roughness. Yes. Accuracy and distortion. Yeah, depending on the design, the more complex the design part, the more difficult to make the part to achieve the accurate dimensions. the part, because you know additive manufacturing has also its own limitations regarding accuracy comparing to the traditional manufacturing process like lathe cutting, drilling, and others. It also depends on the powders. Yeah, as I already mentioned, we should use the spherical or regular type of powders with the spherical shape rather than the irregular shape. Yeah. The processing parameters is also important. Shrinkage and distortion depend on thermal property of the material, orientation of the part with respect to the plate, because it strongly depends on how